Whoa!
Are you here to see Calcmaster Ohm too?
Yes, indeed. I need to ask him about optimization on my box.
I need to ask him about my water bottle. I wrote some good reviews on Yelp about it. I heard it's pretty good.
Come in.
Oh my god. Are you Calc Ohm? Nice to meet you.
Silence. Kneel.
Oh, yes, sir. Well, I need some of your calculus knowledge because I need a 1.8 water bottle to have my energy drink in because I'm a pro tennis.
Silence. I transfer the knowledge now.
I feel smarter already. Thank you. There's another man waiting outside just for you.
Give him the knowledge too.
Oh, thank you.
I need to build myself a tennis court. Well, I only have 550 feet of fencing, and the length has to be twice the length of the width. So, how am I supposed to do this?
So now we know that we have a maximum of 550 feet to use as our fencing. And we'll need two different constraint equations for this problem. Our area, which is our length times our width, or x times y, and our perimeter, which in this case, because I want one side open for people to enter, will be x plus 2y. Now using this, we can say that our maximum perimeter has to equal 550 feet, which means that 550 feet is equal to x plus 2y. Now through this, we can solve for x, saying x is equal to 550 minus 2y. Using this equation, we can go back to the area equation, which we want to find our maximum area, and substitute our x with our given value, which is 550 minus 2y. Now we can simplify this and we get 550y minus 2y squared is equal to our area. Now because we know that to find a maximum of a given function, we have to find the derivative and find the critical points and test out these critical points. What we would do first is find the derivative of this equation, which in this case is 550 minus 4y. Now using this, we set it equal to 0 and we get y is equal to 137.5 feet with no other solution. This means that y has to be the optimal value for our maximum area. Now using this y value, we can go back to the perimeter equation and plug in our y value to find our x value. This means that our x value will be 275 feet, which means in total, the length is 137.5 feet and the width has to be 275 feet.
I need a box to put these rackets in. Well, I have a 20 by 35 inch cardboard sheet. I need to find the optimal height so I can get the maximum volume of the cardboard box. Also, I need to find the maximum volume so I can find out how many paddles I can put into.
Well, in this case, we need to find our optimal height for the maximum volume, given our 20 by 35 inch cardboard box. Now here we're given the volume formula, height times length times width. Now in this case, we can look at our diagram here and find out what the width and what the length is going to be. So we know here that the width is going to be 35 minus the 2h heights given here. And our length is going to be 20 minus the 2h lengths given here. Now we can plug these values back in so we solve for only one variable. Now we're given volume equals h times 35 minus 2h times 20 minus 2h. This simplified gives us this equation. Now we know in optimization, to find the maximum or the minimum of the value, we have to find the derivative of the equation, and then we have to set it equal to 0. So the derivative of this equation will be 12h squared minus 220h plus 700. Set this equal to 0, and we get h equals 4.098 inches. Now that we know our height, we can easily plug it back into the original volume equation here to find our total volume. Once this is done, and we solve it all out in our calculator, we get 1,296.584 inches cubed.
Man, that lab really tired me out. I need a cup for my energy drink. Even better, I need a cup that shows my love for tennis. What's this? A cylinder for a cup is genius. Now that I know that I need to have a cup that's 1.8 liters in volume, all I need to do is find the optimal radius and height to allow me to achieve that kind of cup in the least surface area possible.
So in the case of our cylindrical cup, we have a definite volume of 1.8 liters, and we have to find the optimal radius and height to give us the least surface area for the cup. Now, to make things easy, we need to convert this 1.8 liters into centimeters cubed, which gives us 1,800 centimeters cubed. Now, we need to optimize the surface area, so we're going to be using the surface area formula. The surface area for a cylinder is 2 pi r times h, which gives us the area of the sides, plus 2 pi r squared, which gives us the top and the bottom. We'll also need the volume, which is pi r squared times the height. In this case, we'll need to solve for h. So we know the volume from previous is 1,800 centimeters cubed, and this is equal to pi r squared h. By solving for h, we get h is equal to 1,800 over pi r squared. By plugging this back into the original surface area formula, we get this surface area formula in terms of just r. And in this case, by optimizing, we can find the derivative, find where the derivative is equal to 0, and use these critical points to find our minimum. So first, we find the derivative of the surface area, which is equal to negative 3,600 divided by r squared plus 4 pi r. By solving this, making this equal to 0 and solving for 0, we get r is equal to 6.592. By plugging this r back into the height formula, we get that the height is 13.185. So finally, we get that our radius is 6.592 centimeters and our height is 13.185 centimeters.
I need a box to put all my billiard balls in, just like this one. Trust me, I have a lot.
The volume of the box needed is 65 cubic feet. Now, the sides of the box and the top of the box cost money to cover. And now the sides of the box, they cost $6 per square foot to cover. And the top and bottom of the box cost $10 per square foot to cover. We need to find the optimal dimensions that give us our lowest price, and we have to find out what that lowest price is to pay. In the case of our box, we have to find the dimensions that give us our lowest cost with a definite volume of 65 feet cubed. Now we know that the top and bottom cost $10 per square foot for the material used, and the sides cost $6 per square foot for the material used. We know that the length is double the width, and in this diagram given, we can see that length is equal to 2w multiplied by w and h. So the cost C is given as 10, which is the cost of the top and bottom, times the area of the top and bottom, which is length times width, multiplied by 2, which accounts for top and the bottom. For the sides, we find 6, which is the cost of the sides, multiplied by the area of the sides, which is 2 times width times height, plus 2 times length times height. Now our constraint is given as the volume of 65 feet cubed. Now 65 feet cubed is equal to length times width times height. And in this case, we can plug in our length, which is given as 2w, and we can simplify to where the 65 is equal to 2w squared times height. Now by doing this, we can solve for h giving us h equals 65 over 2w squared. Now by plugging this h in and the l in terms of w back into the original equation, we have the cost function given as just in terms of w. This simplified gives us the cost equals 40w squared plus 1,170 over w. Now, we know for optimization, we have to find the derivative of this and set it equal to 0 to find our minimum cost. So first, we find the derivative. This is equal to 60w minus 1,170 over w squared. Now setting this equal to 0 gives us w equals 2.445 feet. Now, by using this, we can plug it back into the original equations, finding our length, which is 4.89 feet. We can find our height, which is 5.437 feet. And by plugging all these values in, we can go back and find the volume and the cost, which is equal to a total of $717.69.
Well, I only have 550 feet of fencing.
Whoa! Are you here to see Calcmaster Ohm as well?
Yes, indeed.
You missed.